So far we have discussed various facets of enzymes, starting from the chemical and functional nature of the enzymes, the reaction kinetics, methods of immobilization of enzymes, followed by the design and analysis of immobilized enzyme reactors, mainly from the point of view of their application in process industries. And today we will take some examples of these applications, particularly in process industries. That means the use of immobilized enzymes as industrial biocatalysts in the industries. Well, I will try to illustrate with a couple of examples which will give you an idea that why are we looking at the use of immobilized enzyme compared to either soluble enzyme or a chemical catalyst. Now, you will also appreciate that the use of enzymes, particularly for industrial application, are often limited to the sections that are listed here. A major application sector is industrial catalysis, whereby we replace a chemical catalyst for carrying out a chemical transformation to produce a desired product. Typical examples are hydrolysis of starch, hydrolysis of penicillin to produce penicillin or 6-aminopenicillic acid. Incidentally, bulk of the applications are in the field of hydrolysis, that means hydrolytic reactions. Although there are examples where other groups of enzymes have been used in the immobilized form for carrying out industrial processing, but their large scale applications have been so far limited. Bulk of the commercial applications have been in the area of hydrolytic enzymes, except with the exception of glucose isomerase, which is in the isomerase category. The other group of application sector is analytical applications. Of course, enzymes here have a very important role to play because of their specificity, and many of the analytical situations which are enormously difficult in the case of chemical analysis can be handled very accurately and dependably by use of enzymes. And of course, just to economize the operation of the analysis, the role of immobilized enzymes becomes more important. And also the immobilized enzymes will also find use in sensors, that means the electrodes. I mean, if you want to have analytical tool in the form of a online sensor, in that case one looks for the immobilized enzyme preparations which can detect a particular product of interest. Then of course, another area where probably cost or the process economics is not very important is the medical therapeutic applications, where the effectiveness is a very important aspect, and in many cases even immobilized enzymes have found way in medical or therapeutic applications. The typical examples are the urease based kidney, that means dialysis unit, where dialysis units have been modified to include immobilized urease to facilitate the dialysis for the patients who are suffering from kidney failure or things like that. Then of course, another is, as we mentioned some time ago, on use of asparaginase for leukemia patients. Then another application sector is bioseparations. Of course, again bioseparations, the typical example is affinity separations, which are essentially based on the covalent coupling of one of the ligands for effecting the separation process. A very specific method again is applicable either for very high value products or where the number of stages required are very large, they can be minimized to a small number. Then of course, you have a whole range of small applications in different sectors. Probably the most prominent among miscellaneous groups I will like to place is biological waste treatment. Many of the specific systems require intervention of enzymatic catalysis for safe disposal of the waste emerging from a particular industry. And so, but otherwise of course, there might be very small applications here and there where immobilized enzymes might find useful applications. Now, we will be essentially looking at today on the first application sector, where industrial they are used as mainly as industrial catalysts. Now, for their use as industrial catalyst, some of the important factors which are which have to be kept in mind are the yield of enzyme from native source. I think the original enzyme itself has to be chosen which is desirable for any industrial process, both in terms of operational characteristics as well as its the effect of other impurities or other conditions which prevail in the feed stream. They must be able to tolerate it, and the enzyme must be available. When we say yield, I am referring to a term which incorporates the cost part, because higher the yield, the cost can be lower. Then the second probability factor is cost of carrier or and rather reagents for immobilization. The immobilization method, the carrier and the reagents required for immobilization is another factor which contributes significantly to the suitability of the use of an immobilized enzyme preparation for industrial processing. Then of course, activity of immobilized biocatalyst, the final activity which has to be used for catalysis, and of course, operational stability of the immobilized biocatalyst. Again, this is a factor which determines the whole process economics. And finally, as I have mentioned earlier as well, regenerability of the carrier is a factor. You will notice in one of the examples which I will give you today that although the carrier may be very expensive, the cost factor here, as we have mentioned, may be high, but if it is regenerable, the cost can be taken care and does not contribute very significantly to the overall cost of the process. So, regenerability can be a very positive feature, and in most cases that has been the key factor. Now, again I think if you look on the variety of industrial processing that go in processing of foods, animal feeds, what I am trying to say, those industrial sectors which use primarily natural products as the feedstock. Our enzymes are going to play a major role in those industries where the primary the feedstock or the raw materials are from natural source. That means they contain carbohydrate, lipids and proteins, of course, or some other molecules, biomolecules which are often attackable by the enzyme molecules. Now, some of the factors which, in addition to the earlier components of an immobilized enzyme process, which have emerged by virtue of experience in various processes, are also like this. For example, if you consider the enzyme and the two or rather the three factors, the cost, the reuse and the stability, then the immobilized enzyme systems are very suitable for high cost enzymes, where the cost of the enzyme is very high. Of course, in the case of enzymes with low cost, even a batch system with soluble enzyme may be suitable, and in fact, as I will like to tell you that particularly for example, an enzyme like alpha amylase, where the cost, which is one of the example of one of the lowest cost and caustic enzymes, essentially is used in a batch in a soluble form in a batch reactor, because you can afford to discard it after, you need not recover it, whereas high value enzymes are most suitable to be used in the immobilized form. And of course, here I am not, when I say column system, I am covering both either a packed bed or even it could be, depending on the process, a CSTR also, but of course here the column gives only a column. Then the reaction control. The reaction control in the case of soluble enzyme and the batch immobilized enzyme is usually difficult, which makes it very easy in the case of a continuous flow immobilized enzyme reactor. The control of the enzyme reactions is rather difficult in the case of soluble batch processes, soluble enzyme batch processes, or even immobilized enzyme batch processes, and the control is much more effective in the case of a continuous flow reactor using immobilized enzyme. Of course, the product purity also has a role to play in decision making of the use of immobilized enzyme, or otherwise product purity can be very high in the case of immobilized enzyme used in continuous reactors, because there is no contamination from the proteins or the enzyme protein likely, or the some of the side reactions are likely to take place in the case of the continuous reactors, and the residence times are usually lesser than the soluble enzyme or the batch reactors, because the advantage of the smaller residence time in the continuous reactor, as well as the absence of any contamination from the enzyme protein, provides you a product which is much more pure compared to soluble enzymes or an immobilized enzyme in a batch system. Of course, the equipment part is slightly unfavorable in the sense that in the case of a continuous flow immobilized enzyme reactor, the initial capital investment for equipment may be comparatively higher compared to a batch soluble process or a batch immobilized process. Of course, the same thing applies to automation. In the case of batch processes, there is no automation, whereas continuous processes can be automated, and which can make a lot of saving in the labor cost. And running cost essentially, or also that means essentially the labor cost, again are also relative per unit weight or volume of the product are relatively low in the case of continuous systems using immobilized enzyme. And of course, the processes with immobilized system can be easily scaled up compared to the batch processes, which might find variations from batch to batch. And so these are the various parameters like the enzyme itself, the reaction, product, equipment, running cost, and advantage of scale. And obviously, one has to analyze a given process on the basis of these parameters and then take a decision whether it is desirable to go for a soluble enzyme based system, immobilized enzyme based system, or immobilized enzyme continuous system. Now, the first example that I want to illustrate with the use of immobilized enzyme is the production of L amino acids by immobilized amino acylase. Incidentally, I mean this example has a interest in the sense, and why I chose was that this was probably the first commercial process used anywhere in the world using immobilized enzymes. The same process was being used in Japan using a soluble batch enzyme over a period of about 10 years, and they were producing L amino acids by using your amino acylase soluble enzyme produced from the microbial sources. But then in those soluble enzyme batch processes, the problem of purification was very severe. That means usually the product stream after the batch process will be contaminated with the enzyme. It has to be removed, because these amino acids which were produced were essentially useful either for food applications or animal feed or sometime in pharmaceuticals, and therefore you cannot leave any unconverted or unused proteins in the feed stream, and the number of stages involved in purification essentially will lead to loss of yield for the amino acid as high as 50 to 60%, and therefore obviously when you are going to lose almost 50% in the amino acid in recovery process, the cost is going to be double, and plus the cost involved in the purification itself. And therefore there the shift from the soluble enzyme to immobilized enzyme became a very great incentive to bring down various facets of cost and having a much cleaner process which can give a better quality product, much higher yield, ease of purification, and all those advantages. Now, normally these amino acids, when they are synthesized by chemical route, they are reciproc mixture of D and L, and one of the they get in the final stage as DL acyl amino acid. Now, this, when I am saying L acyl amino acid, this R could be anything, the whole range of amino acids, and specifically of course in most cases depending on the amino acids there is a corresponding amino acylase. Of course, some of the enzymes are little less specific, that means they can act upon 2 or 3 different amino acids, but most of them are very specific to a particular R group, particular amino acids, and they are produced, and the DL acyl amino acid can be hydrolyzed by the enzyme, suitable enzyme which hydrolyzes or recognizes the particular amino acid to give the L amino acid, the it gets deacylated and you get L amino acid, and D form remains unconverted, untouched. And of course, essentially that means what happens, you get a mixture of L amino acid and D acyl amino acid. Now, these two molecules essentially have a very distinct difference in their solubility at different pH, very distinct. So, by adjustment of pH and taking advantage of solubility, the L amino acids can be easily crystallized and produced in a very pure state without much of headache of removing proteins or deactivation of the enzyme or separation of the unconverted D form. Now, as a matter of fact, the same process also gave a side effect, or rather a very important tool to produce even D amino acids, because the D acyl amino acid can then be which is separated out after crystallization, can even be chemically hydrolyzed to produce D amino acid. There is no problem, and D amino acids are used as raw material for many of the keto acids which are used as raw material in pharmaceutical industry. Well, of course, until then, from the racemic mixture we were isolating L amino acid and the balance was almost wasted. Now, here the process economics becomes very attractive, because while you are able to isolate L amino acid with a much better yield, you are also able to use the residual material D amino acid, either if it is required for keto acid, or alternatively this can be again racemized chemically, by just chemically means just by change of pH. Essentially it gets racemized again to a DL mixture, and the whole process can be repeated till almost 100% of the amino acid is recovered in the L form. And of course, you get the corresponding fatty acid also produced in the system, which is separated from the mixture. Now, to do this reaction, a number of studies, I am sorry, I think but I will be able to point it out, of course, the important points. What it refers to, this table refers to that the enzyme, the amino acylase from Aspergillus species was isolated, and one of the first enzyme which was isolated was based on methionine acylase, and methionine acylase from Aspergillus oryzae was isolated and was immobilized by using a variety of methods. And if you look into the list, they had used physical adsorption, ionic binding, covalent binding, cross linking in the presence of carrier, lattice entrapment and microcapsule entrapment. Almost virtually all the methods were employed to immobilize the methionine acylase. Incidentally, if you compare all the methods based on the initial quantity of amino acylase used, the activity recovered in the immobilized form and the yield of activity, the method based on immobilization of amino acylase by ionic binding to DAE Cefadex was proved to be the best in terms of its enzyme activity, 713 units per gram or whatever units they have used, and with a 58.9% yield of the recovery of the activity from the soluble enzyme, as compared to various methods where the activity recovery as well as the final activity of the immobilized preparation was much lower. Of course, the comparable ones were only next were entrapment in polyacrylamide gel, and of course covalent binding to some aryl amino glass, diatization, again covalent binding. But of course, if you look into the cost of immobilization in terms of cost of reagents, covalent binding was expensive. Of course, gel entrapment was cheaper than Cefadex if you consider, but when you look at the operational advantage, you will notice that even an expensive carrier was desirable and acceptable. Now, for designing the whole process, commercial process, basically they looked at really two major parameters effectively, although as we can notice that now today we have a much better strategy and understanding of the various design parameters for the immobilized enzyme reactor, but in the process two major parameters were considered: the effect of space velocity on the concentration of amino acid in the effluent. Space velocity essentially is analogous to dilution rate in a CSTR, And so you will notice here that in the case of the same enzyme was able to sort of act on methionine as well as phenylalanine. So, in the two cases, and on the right hand side is the hydrolysis of L form. In fact, at a concentration of 0.1 molar, the reaction is stopped when almost 100% hydrolysis of the L isomer was completed, and the kind of profile you get is almost a sigmoidal profile, and at a space velocity of approximately about 8 hour inverse, the reaction was complete, and that means 100% of the L isomer was hydrolyzed and recovered. Now, if you notice here some of the experimental conditions, aminoacylase was immobilized by ionic binding to DHF(X). 0.2 molar concentration of the substrate was used, containing 5 into 10 to the power minus 4 molar cobalt salt, which acted as a stabilizing agent, stabilizer for the enzyme, and reaction temperature was 50 degrees centigrade. And now another parameter which they considered was the pressure drop. Probably that they considered to find out the height of the column, and they noted also that the pressure drop across a column bed followed a very typical the fluid dynamic expressions which are available, and it was proportional to the space velocity as well as to the length of the height of the column. And essentially they selected the height of the column based on the pressure drop limitations, so that they do not have to face very severe pressure drops. Particle size was chosen according to that. They did not make any further analysis based on internal mass transfer or anything else. The space velocity and pressure drop are the key parameters that were studied, based on which the whole reactor system was designed and operated continuously. Now, this is a process flow diagram that is still in operation in Japan. Of course, has been in operation since 1963, the first sort of system which came into being and still being operated. Now, as you notice here, this is the storage tank for the acetyl, the racemic mixture which comes, let us say, from chemical synthesis. Now, here we just pass it through a heat exchanger to maintain the temperature 50 degrees and pass through a immobilized enzyme column. And of course, there are arrangements for temperature, pH and flow rate control. Then the final product from the packed bed column goes to a concentrator, where it is concentrated just to take advantage of solubility and crystallization, and it gets the L amino acid gets crystallized, separated, and crystalline L amino acid is separated. And obviously, crystallization being used as a method, one is very it's a very favorable method for purity of the product. And the D-acyl amino acid then is separated and is taken to a separate tank for racemization, where pH is changed and racemization occurs, and this mixture is again fed back to this tank, is a racemic mixture, and again go. And as a matter of fact, the whole process produces almost a conversion of 100% conversion of DL to L amino acid ultimately. And of course, alternatively there have been attempts also where the D-acyl amino acid can also be produced by hydrolysis, chemical hydrolysis, to produce your D amino acids, which are also raw material for keto acids in the fermentation industry, in the pharmaceutical industry. Now, the operational stability and regeneration of the carrier, I think the one point which I was addressing. As you notice that these columns, the actual data is that they have quite a stable performance, in the sense that in about let us say more than about 32 days of time of continuous operation, more than 70% of the activity is retained. As per their plan, they regenerated their material after one cycle at about 72% of the activity was lost. They stopped the reactor, added more enzyme, whatever loss has taken place, 30% and 28% enzyme was additionally added and accumulated, so that the enzyme reaches again to the original loading capacity. Again the reactor was started, and of course this can also be done by using multiple columns. Instead of using a single column of large capacity, one can break down the total volume in smaller capacities and staggered operation. we will try to look at the operational part also subsequently. And basically today in practice, although while they operated a single column with a break in between of the operation, but today most of the immobilized enzyme columns are operated in a multiple column and staggered startup mode, so that the productivity, you do not have to make a break in between, and the productivity and conversion can be maintained almost constant within a narrow range over a period of time. And the regenerated enzyme again went down and can be again regenerated, and this cycle is continued over almost about 32 days period. And now you notice that, now I think let us look at the cost part, their process economics, and this was the data given by presented by the authors themselves who carried out the commercial operation. And if you compare the production cost of L amino acids by batch which was being operated originally, that means prior to 1963, it was a batch soluble enzyme process and a continuous immobilized enzyme process. Now this is a comparison, and this is the fraction of the relative cost. So first thing, I think first point to be noted is that the cost of production of the product per unit basis has come down to 59%. Whatever was the original cost, 100% of this L amino acid, and this is the case in the case of methionine. In fact, these data are in the case of methionine, and a similar analysis applies to almost all amino acids. The cost of production per unit quantity of the product comes down by about 69% total cost. Now if you see the breakup, you will notice that there is a significant change in the cost as a result of the raw material, that means racemic mixture of amino acid, DL amino acid, acyl amino acid. Now the cost is reduced significantly, and that is the bottom shaded portion, and that is basically because of the increase in yield, because the recovery has improved. So per unit cost as a result of raw material consumption has decreased. The second part is the enzyme cost. Of course, as expected, in the case of soluble enzyme there is no recovery of enzyme, and the cost of enzyme in the case of immobilized process is very small, almost negligible compared to this. The third component, there is significant reduction in the labor cost. Another factor, I think the two major factors which contribute to reduction of the cost in immobilized processes are enzyme and labor. So basically I think that also gives us a clue, the enzymes which are more expensive, I think immobilized processes are more favorable. If let us say if the enzyme cost is not very high, this is not going to make a great dent on your process. Similarly, the recovery process involving labor, if it is very tedious, again immobilized enzyme processes will be more favorable. So the labor and the enzyme cost are the major factors. Then of course fuel cost, there is hardly any difference, it makes no difference. And then another factor is, the blank portion, the cost of the carrier, which is an additional input in the case of immobilized enzyme which did not exist in the case of soluble enzyme. Although DI Cefatex is a very expensive, considered to be probably one of the most expensive carriers they tested on all material, but the total life of the carrier which they were able to use is almost 5 years. And if you distribute on the total product formation, that cost contribution is very small. And therefore I insist regenerability of the carrier is, and because they can regenerate the carrier as and when the enzyme activity comes down, even they can dissolve it, they can reabsorb it, and the enzyme the carrier is fairly sturdy, doesn't get degenerated. It can attain its own absorption, and they were able to use easily for periods up to as high as 5 years. Of course, during process there might be some handling losses, and which might reduce some quantity, and this factor is primarily because of the handling losses during the regeneration process. So this gives you a picture of the process economics and the contribution of different factors in the operation of an immobilized enzyme process. Another example that I like to illustrate is also an organic molecule production of L-aspartic acid. Now L-aspartic acid is a molecule which is used in the food industry and pharmaceutical industry, and this can be produced by aspartase, an enzyme, lyase enzyme, which acts on fumaric acid and ammonia to give you the L-aspartic acid. And of course, the work was reported by Tosa and others in biotech bioengineering in 1973. I think you may like to go through, and I will suggest that some of the references which I have given, if you just go through them, you will find some of the details of their experimental details, how did they arrive at the final decisions. Now, if you look the same data as we looked in the case of aminoacylase, in the case of aspartase, they also carried out on a variety of immobilization methods, including physical adsorption, ionic binding, covalent binding, and entrapment. Now, incidentally, you will notice that the activities of the final enzyme preparations and the percentage yield of the activity from the during immobilization are relatively very low here compared to the original enzyme used. If you notice that the percentage recoveries are very low, excepting in the case of entrapment in polyacrylamide gel, which resulted in the yield of about 29% compared to aminoacylase, where the activity recoveries were of the order of 50% and more. Here it is only 29%, but still 29% is the highest, and probably one has to accept it, but otherwise the activities were not, and that is one of the reasons I think, just to illustrate the point, that although they started with using immobilized aspartase for producing aspartic acid, but they discontinued very shortly and shifted to an immobilized cell process, where these losses were not there. They immobilized the whole cell itself, and the activity, the whole activity was retained, and they could use, and the process was much more economical than the immobilized enzyme process. But of course, this is just one example where I want to illustrate that in what conditions you have to shift over to. One is that, I mean, if there is an enzyme which is intracellular and the recovery and purification cost is very high, probably immobilized cells will provide an answer. On the other hand, if the immobilization method is not able to produce, you are not able to get a good method which can recover a good yield of enzyme, or the final activity in the high amounts, in that case also immobilized cells may be a easy or a suitable answer. Now, if you look at the same enzyme aspartase operation, continuous operation in the packed bed reactor, now this gives you the percentage of the L-aspartic acid recovered in the product stream, and they carried out at two different substrate concentrations, 0.2 molar and 1 molar ammonium fumarate. Two different substrate concentration of the concentration, and you notice that the performance over the operating time is totally different as a function of even substrate concentration. And you notice that in the case of 1 molar ammonium fumarate, it is able to reach about 50% activity in 20 days time. It goes down to 50% activity in 20 days time. When you take lower substrate concentration 0.2 molar, the activity loss is much higher, and over the same period of time, instead of 50%, it reaches to about 25%. And essentially this is a case where if you recall, we discussed the substrate dependent enzyme decay. We discussed two cases of enzyme deactivation during continuous operation of the reactor. One was substrate independent, where as in the earlier case, in the case of aminoacylase, substrate concentration plays no role and the deactivation constant is predominant, but in the case of the aspartase, it is a substrate dependent deactivation, and higher the concentration of the substrate, the operational life is comparatively better. This is the operational profile. For 0.2 molar, it deactivates much faster, and you see that in 20 days time, almost 25% of the enzyme, only 25% of the enzyme is left, 75% has got deactivated, and here in the same period almost 50% of the enzyme is present at a higher substrate concentration. So therefore, one has to also look about the deactivation kinetics, because that will also play a important role. The third and perhaps the a very simplistic example is of the hydrolysis of starch for the production of glucose. Now, essentially the hydrolysis of starch goes through three different stages: gelatinization, usually a heat treatment process; starch gel, which is acted upon by alpha amylase. As I mentioned in the beginning itself, it is a very economical, very cheap enzyme cost wise. When I say cheap, I am referring to comparable to the cost of other enzymes, and therefore it is used usually in soluble batch process at a very high temperature, because even the alpha amylase is a very thermostable enzyme and can be operated at temperatures even 100 plus, and therefore the gel gets immediately liquefied by, and it is a very fast enzyme. The specific activity is very high, and therefore the enzyme very speedily converts the gel into a liquefied starch, which is essentially a mixture of dextrins, small chain length starch molecules. Chain length varying between not more than 10, usually 6 to 8, but the dextrins should not have more than 10 glucose unit linked together, and then these dextrins essentially, now this is a step which is a rate limiting step in the whole process. The dextrins to glucose by amyloglucosidase or glucoamylase, it is called as glucoamylase also, and now this has to be, now this step essentially has been carried out using immobilized enzyme in continuous reactors, so that one can take advantage, and the whole process can be controlled by this step. Now, of course, a very large number of studies have been carried out on immobilization of glucoamylase. One of the very strong design, the process which was designed in US by Beetle and group, which was based on adsorption of glucoamylase onto porous silica. Porous silica beads were taken and the enzyme was adsorbed onto that, and obviously you will appreciate that the cost of the product is not very high. So, one cannot afford any expensive immobilization method, even if the operational stability is not very high, it does not matter. Now, but one of the major issue with the hydrolysis of starch essentially is in the form of the viscosity of the feed, because starch hydrolysis is usually done at a very high substrate concentration, usually 30 to 40% dissolved solids, which makes a very viscous syrup during operation, and this viscosity causes a significant problem as far as the pressure drop is concerned in packed bed reactors, and therefore not many packed bed reactors for this step are operational today, because use of packed bed reactors with a almost 40% total solid syrup is highly energy intensive and is usually avoided. And as an alternative, some people have even proposed to use a CSTR, whereby one can use a stirred vessel, a classical system where one can add substrate maintain the feed of substrate feed at a constant reservoir, and a agitator paddle, then a stone filter just to retain the immobilized enzyme particles, and the material is filtered through this stone filter and passes through a peristaltic pump to a charcoal column, which removes coloring matter or other impurities in the, of course depending upon the further application, it may be deionized and other operations may be done, concentrated, and of course you can collect the product. And of course this was the system which was reported for glucoamylase immobilized on DI cellulose by ionic binding. Again the DI cellulose also is a very stable carrier which can be regenerated, although no such commercial process is operational in the case of glucoamylase, mainly because of the process economics. Even most of the processes which are in use, they are using adsorption onto clays, bentonite or some other clay, not any expensive or well defined matrices. So, these are some of the illustrative examples, not that these are the only processes which are operational. A large number of other processes which are operational commercially all over the world are, one is penicillin acylase, which gives you from pen G or B plus H2O. Hydrolysis of pen G or B goes to 6-APA, and the 6-APA is an intermediate for a variety of antibiotics, the semi-synthetic antibiotic, and they are commonly used. Now, many of the immobilized penicillin acylase system have been produced worldwide and marketed. A large number of products are available commercially. In fact, in India also, is a major producer of 6-APA in fact, and which produces a significant quantity of 6-APA, but bulk of the immobilized enzyme preparations are imported incidentally. And of course, the products are available from many countries, Astra in Sweden or Beachem in UK, Toyozozo in Japan, or even for example Carrier, some industries which are making their own immobilized enzymes here in house, they are also importing the carrier. Of course, it makes no difference if you import the carrier, bulk of the cost is already paid, and like from Toyozozo Japan. And this is another example where immobilized enzymes are used commercially and in very large quantities. Then you have inversion of sucrose. A very typical example or a very typical illustrative example from the point of view of India. You see, world over the production of a glucose fructose syrup is mediated through corn. Corn as a starting material, corn is hydrolyzed to produce glucose, corn is a source of starch, corn to starch to glucose, and glucose isomerization to fructose, and a equimolar mixture of glucose and fructose. But in India, corn, a good quality corn meant for this purpose, that means sweet, what we call as sweet corn, is usually not available, and the relative cost of corn is also high in India because it being a staple food. So it does not meet the requisite commercial requirements, and but still to produce glucose fructose syrup for many of the food industry applications, and the major consumer of glucose fructose syrup in India is the beverage industry. In fact, most of the products, for example the beverages particularly of Pepsi and Coke, they are based on glucose fructose syrup. They do not use sucrose as a sweetener. Because of the use of glucose fructose syrup in their parent countries, principal countries, their processes are based on, they need glucose fructose syrup, otherwise the product taste and product specifications will change. And so essentially in India they are using the inversion of sucrose, using invertase, because sucrose is available at a fairly low cost, and inversion of sucrose from sucrose by invertase is the process which is used in India, and again in the immobilized form. And there are a number of at least 3 or 4 major units which supply glucose fructose syrup produced from sucrose. Then another process is for malic acid from fumaric acid. The fumaric acid on hydrolysis by fumarase gives malic acid, L-malic acid, which finds applications in food industry as a food additive. As a matter of fact, the conventional method other than this for malic acid is only isolation from fruits, which obviously has to be very, very expensive compared to this method, but fumaric acid is available as a synthetic organic acid, and from fumaric acid it can be converted to malic acid for a variety of applications. Then the brewing industry uses for chill proofing of beer. Now during storage of beer after fermentation is over, it is clarified and stored for some time, and during storage it develops a haze, which is essentially, this haze is as a result of reaction between polyphenolics and polypeptides, because both these molecules come from the basic raw materials. You use barley or any other cereal adjuncts which are initially started to make the mass. Now they contain certain polyphenolics and polypeptides, and they react during storage to give you a haze, and of course a hazy beer nobody likes. One wants a sparkling clear beer, and this clarification or the chill, what they call as the term they call as chill proofing, is essentially done by immobilized papain, a proteolytic enzyme papain, a proteolytic enzyme which is immobilized and used in a column to remove, because it essentially degrades polypeptides, or even polyphenol oxidases also have been used, mixture of the two, so as to degrade those molecules and remove the haze, which can be filtered and the clarified beer is available. Then another application in the food sector has been on lactose free milk. Lactose free milk. Now milk contains primarily lactose as a principal sugar. Now, and this lactose is essentially a sort of a undesirable sugar for certain adults. Of course, in India we are used to take milk and sugar is assimilated, but in many countries the population is not able to assimilate lactose, and it causes diarrhea and kind of clinical symptoms, and therefore people cannot take milk. In those cases they produce a lactose free milk by action of beta galactosidase, on milk, which hydrolyzes the lactose into galactose and glucose. So essentially, and now galactose and glucose essentially are assimilable, are the monosaccharides which can be assimilated, and without losing any of the nutritive value, the milk can be made free from lactose, and such products are available for consumption in some of the countries. And so these are, and of course there are many other smaller applications, but these applications essentially require the idea of methods of immobilization, and their application for reactor design, keeping in view the variety of issues that we have discussed in the past.